Hello everyone, today let's take a look at QP149 where we have N boxes and K cards. The cards are numbered 1 through K, and on each turn you deal a card from the top of the deck and place the card in a box uniformly at random. After all the cards have been placed, consider the box that contains the card number J. What is the expected value of the smallest numbered card in that box? So essentially what's happening here, if these are my N boxes, well then I'm going through all my cards that are numbered 1 through K. So for card number 1, right, I'm going to have a uniform chance of placing it in any of these boxes, right? So it could go in this one, it could go in this one, it could go in any of them, right? So because it's uniform, the probability of going in any box, right, is going to be 1 divided by n. So for card number 1, I have a 1 out of n chance of going in this box. I have a 1 out of n chance of going in this box, right? I have a 1 out of n chance of going in this box. And then for card number 2, I'm going to have the same story, right? I have a 1 out of n chance of going in this box. It's going to be independent of basically where we place number 1, right? So we can go in any of our boxes again with 1 out of n probability. And then we have this special card, which is number j, right? So maybe j is equal to 4, maybe it's equal to 5, right? It's just going to be some number between 1 and k, and that card also has a 1 out of n probability of going in all of our boxes. So once we've dealt out all the cards, we're basically looking at the box that contains j and asking what is the expected value of the smallest numbered card within the box that contains j. So if I let x be the value of the smallest numbered card in the box containing j, we're trying to find the expected value of x, the definition of expected value. We sum up over all the possible values that x could take. So what could it take? It could be anything from 1, right? If card number 1 is in the box containing j, well then that's going to be the smallest numbered card. And then the maximum that the smallest numbered card could be is j, because j is already in that box. So x can take values between 1 and j. And then definition of expected value, we take x, we weight that by basically the probability that x is equal to that little x, so that card being our minimum. Now we essentially just have to find this probability distribution right here. We could start working it out. The probability that x is equal to 1 is just the probability that 1 ends up in this box containing j, because if 1 is in a given box, then it's automatically going to be the smallest numbered card in that box. So that probability is just going to be 1 on n, the probability that 1 is within the box containing j. Now the probability that x is equal to 2 is just going to basically be the probability that 2 is in this box with j and 1 is not within that box, because if 1 was in that box, well then it wouldn't be the smallest numbered card. 2 wouldn't be the smallest numbered card, right? So this is the probability that 2 is in that box, and then the probability that basically 1 is not in that box is going to be n minus 1 on n. And you can keep going like this, just find the pattern in this probability distribution, plug it in and solve for this, but this is going to be a lot more complicated than if we did it using the tail sum. So oftentimes when we're summing up these big things, right, we're taking some geometric type of probability, or when we're just finding basically the minimum or the maximum, you'll find that's easier to use basically the tail sum formula. So that's what we're going to do. So about the tail sum from QP122, where we prove that, right, this is just going to be equal to the sum from basically x equals 0 all the way up to infinity of the probability that x is greater than that little value x. And now this makes it easier because now we don't have this x in our formula that we're going to basically take a long series of, right? So it's going to be a lot simpler this way. And now the probability, let's just do a few of these. What's the probability that x is greater than 1? Or actually, we should start with the probability that x is greater than 0 because we start at 0, right? So what is that probability? Well, j is going to be in this box no matter what, because we're looking at the box containing j. So it's going to be at least j. So the probability that the smallest numbered card in the box containing j is greater than 0 is going to be 100%. Now let's look at the probability that x is greater than 1. The probability that the smallest numbered card in this box right here is going to be greater than 1 is just the probability that 1 is not within this box, right? That probability is going to be n minus 1 divided by n. Now you can see why this tail sum is going to be a lot simpler to do, right? What's the probability that x is greater than 2? Well, that's just the probability that both 2 and 1 are not in the box containing j, right? So it's just going to be n minus 1 on n times n minus 1 on n, so n minus 1 on n squared. And now you can see the pattern, right? The probability that x is greater than 3 is going to be the probability that 1, 2, and 3 are not within that box, which happens with probability n minus n on n for all 3 of them, right? And they're independent, so we're just going to cube it. So now we understand the pattern of this distribution right here. It's just going to be n minus 1 on n to the power of our little x that we're summing up over. However, this pattern doesn't work for all 0 to infinity of our terms, right? Because after j, right, the probability that x is greater than j, first of all, that's just going to be equal to 0. And the reason for that is just the fact that j is already within this box. So the probability that the minimum card is going to be higher than that doesn't make any sense, right? Because j is in it. So at most, the minimum value within this box is going to be j. The probability that x is greater than j is going to be 0. So we're going up here to basically j minus 1. Now we just have a nice geometric series, which we know how to take the formula of because we did QP number 64. In that question, we proved that the sum from 0 to some value of m of some ratio raised to that power of our iterator, in this case it's x, is just going to be equal to 1 minus r to the power of m plus 1 divided by 1 minus r. If you plug in r values to that formula right there, we have j minus 1 that's basically acting as m in that formula, and we have n minus 1 on n, which is acting as r in that formula, right? So when you plug them in, we have basically 1 minus r, which in our case is n minus 1 on n. That's going to be raised to m plus 1, right? And j minus 1 is basically acting as m. So this right here will just be j, and then that's going to be divided by 1 minus n minus 1 on n. Now 1 minus n minus 1 on n, that's just going to be n on n minus 1 on n, right? So that's just going to be 1 on n. So essentially the final answer is just going to be n times 1 minus n minus 1 on n, and then that's going to be raised to the power of j, right? So this right here is going to be the formula representing our final answer, the value or the expected value of the smallest numbered card in the box containing j when we basically have n boxes and k cards. You can see that k doesn't even appear in this formula. And the reason for that is that it doesn't matter how many cards we have, right? Because j is already going to be in the box that we're conditioning on, right? So at most, the minimum is going to be j if no other cards are in that box, right? So we don't even care about the cards greater than j. But yeah, this is just a good application of the tail sum. Again, this is our final answer.